Hi, today let's solve the problem of removing every kth node in the linked list. So we are given a linked list and a number k. Our task is simple. We gotta remove every kth node from the list. Here, let's say k is, let's say we have k as 2. So it means we should remove every second node. Let's say we have this linked list 1, 2, 3, 4, 5, 6, 7, 8, and null. Okay, we have k is 2. So here nodes 2, 4, 6, and 8 will be deleted. Therefore, the expected output will be 1, 3, 5, 7, and null. Okay, so let's see how we solve this. Firstly, we got to handle the most important edge case. If suppose k is equals to 1, that means we would be removing every node. So the answer is simply null because the list becomes empty. Next, for simplifying deletion logic, we should introduce a dummy node. So let's say we have a linked list 1, 2, 3, and so on up to null. Okay, 5 and null. So basically we introduce a dummy node, and this will be the head for that linked list. Now this dummy node will help us handle the edge case cleanly, especially when deletions affect the head. So our traversal will start from the dummy node, and let's take a fresh linked list. Suppose we have k is 3, and we have a linked list as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is a long linked list, but never mind. Okay, so we use a pointer called current starting at the dummy node. So let's introduce a dummy node, and the current will be starting from the dummy. And we also maintain a counter that keeps track of all positions. So we have a count. So basically, the count that we use is count equals to count plus 1 modulo k. Okay, so what happens is as we traverse the list, we increment our counter. So instead of counting up to k manually, we use modulo. But why are we using count equals to count plus 1 modulo k? So this lets us detect every kth position without resetting or without any extra checks. So whenever modulo becomes 0, we know we've reached the kth node and therefore we should delete it. But how do we get the idea of using only this particular formula? So the idea is derived by realizing that we only care about the positions relative to k, and we don't care about the absolute count at all. And modulo naturally cycles numbers from 0 to k minus 1. So when it resets 0, it clearly signals us that this is the kth step, and therefore we need to delete that without any manual resets. All right, let's quickly dry run it. Suppose we have a linked list, say dummy 1, 2, 3, 4, and null, and current is pointing to the dummy variable, and we have initially count initialized to 0. The first iteration, count becomes 0 plus 1 modulo 3, which is 1 modulo 3, that is 1, because initially count is 0, so we are replacing it here. Now since count is not equals to 0, we move forward, and now I am at node 1, and we are not performing deletion yet. Now we are coming to the second iteration. Here count is 1 plus 1 modulo 3, that is 2. So even here count is not equal to 0, so we move forward. Still counting, no deletion. Now coming to the third iteration, we have count equals to 2 plus 1 modulo 3, that is 3 modulo 3, that is 0. Now we delete current dot next. So now this will be deleted. Okay. So this is how the entire count equals to count plus 1 modulo k works. Now we got to perform a deletion. As you already know, deletion in a linked list is just pointer manipulation. So we skip the node by doing current dot next is current dot next. No shifting, no extra memory, just links. So basically the step turns like 2, 3, 4. Current was here, and this becomes as 2 and 4. 3 is removed. Okay, we repeat this process until we reach the end of the list, and every kth node is removed in a single pass. So to summarize the approach, we use a dummy node, traverse once, delete nodes using a pointer rewiring, and never use extra space. Therefore, the time complexity will be big O of n because we traverse the list only once, and space complexity will be big O of 1 since we only use pointers. This makes the solution optimal and interview friendly. This is a classic linked list problem that tests pointer manipulation. Once you visualize it, the solution becomes very clear. Now let's look at the coding approach. All right, let's quickly code this approach up. So we are defining a solution class as expected by the problem, and this function receives the head of the linked list and value k, and it should return the modified list. So the first edge case that we discussed is if k is equals to 1. That is, if k is equals to 1, it means we need to delete every node, so the linked list becomes empty and we return none immediately. Okay. And the next thing we need to do is we need to create a dummy node to simplify deletion logic, especially when nodes are near the head that are to be removed. So dummy is node of 0. Okay. And the dummy node points to the original head of the linked list. So dummy dot next is head. Now let's initialize a pointer. So I initialize a pointer called current starting from dummy nodes, so I can safely modify next pointers. So current is pointing to the dummy node, and we need to initialize a counter as well that will help us track every kth position using the modular arithmetic. So let's say we have count initialized to 0. Now about the traversal loop, now we traverse a linked list using the current pointer that reaches the end. That is, if while current, we increment the counter and take modulo k, so whenever count becomes 0, we know we have hit the kth position. So count is count plus 1 modulo k. All right. Now if count is 0, it means that we reach we if the count is 0, it means the next node is the kth node and that should be removed. So if count is 0 and count dot next exists, means we need to remove that node. And we also check if right here we checked if current dot next also exists, because we don't want any null pointer issues. So current dot next equals to current dot next. This will ideally remove the kth node. So we are deleting the node by just simply skipping it. So this rewires the linked list without using extra memory. If that's not the case, else current is current dot next. If this is not a deletion step, we simply move the current pointer forward. Now finally we return the original head, which points to the updated linked list. Now let's go ahead and run the code. Sorry, this should be current dot next. Yeah, let's run it. So as you can see, the first the input list is this, and after removing every second node, we are left with this. Similarly, this is the input node, and after removing every third node, this will be this. And suppose we are removing every first node, that will be returning null. Thanks for watching.